Hello dear friends, now we'll talk about the capillary rise or fall inside, means the rise or fall of a liquid level inside a capillary, and this phenomenon is also called as capillary action. Okay, so if they ask you about capillary action, it will have the same answer. Okay, so we'll understand what is actually the why the liquid surface rises or falls inside a capillary action. Okay, so this happens only for a particular dimension of a capillary, but that analysis is beyond your scope right now. So if you see, okay, I will start it. Before this, you must understand that if you take any concave surface, if you take 2 points A and B, we have seen that if the concave surface, here the pressure is PB and here the pressure is PA, you must be clear that PB should be greater than PA. Okay, if the surface tension is not neglected, okay, you should remember this. Okay, it doesn't matter where the liquid is, but the concave and convex surface, the pressure on concave side is always higher than that of the convex side. Okay, so try to remember it. So let's say this is the liquid tub. Inside, this is a complete liquid, and now what I will do, I will put a capillary inside it. Okay, just focus it on. So here this is the surface, and now first I am talking about capillary rise. Okay, first we will talk about a rise, and it happens mostly when the surface the pair is glass and water. For this pair, what happens, the liquid inside it rises. Okay, comparatively its height is more than the normal liquid surface. Okay, so that is called as rise. So why it happens, we'll understand it first. So let's say there are 2 points, this is A point and this is B point, and we know that when the glass and water, this is the pair, the shape of water surface inside the capillary is like this, isn't it? So it is like this. So this is the point B and this is the point A. Okay, if you take any corresponding point here, okay, at the same horizontal level, if you take any corresponding point, that is C, let's say, according to the law of hydrostatic, you must know that PB should be equal to PC. The PB should be equal to PC. Okay, but what happens, okay, according to hydrostatics, this must be true. Okay, but what happens if you see here, this is at the concave side and this is at the convex side. See, it is very easy to differentiate between them two. Okay, don't overthink about it. This is concave side, this is convex side. So you must be knowing that PA is greater than PB, isn't it? So what it does mean, that pressure at B is less than that of at point A. Okay, you should remember this. Now if I take this point A and if I take one more point here D, you must be sure that PA should be greater than should be equal to PD, because they are horizontal at horizontal level. And if you look at the distance between this point D and D and C, you can say that yeah, it is also equal to PC, because this is not that much distance and this is under the water or under the liquid, but not up to that much depth. Okay, if the point C were here, then you could not say this. Okay, but the point C is nearly at the it is approximately at the surface, so you can say that these two surface the pressures are equal. Okay, so PA is equal to PD because they are horizontal level, and PD is almost equal to PC. Okay, you can say like this, isn't it? Just try to understand that. You rewind this video and just concentrate what I said here, why I equated all these pressures here. But if you see, PB is less than pressure A, or you can say PB is less than PC, because these three are equal. And if PB is less than PA, it means that it is less than PB is less than any of the pressures here, PA, PD or PC. So I am writing here PB is less than PC. So what will happen now if PB is less than PC, but they are at horizontal level, isn't it? Though they are at horizontal level, but they are not having equal pressures. So what will happen if you take any other point? It will be at the same condition. So the water will try to rush into this tube from the higher pressure to lower pressure, isn't it? Means from C to B. And that's why what will happen, after some time you will see the condition will be like this. The point C will be here, the point B will be here. The point C will be here. Due to this water rushing inside, what will happen? It will rise. The level of water will rise into it. Okay, this is the method of pressures you should understand here. Okay, this is the basic concept you should know, then you can write the complete answer. So this was all about rise. Okay, now if I'm talking about the fall, so I would take the example of mercury and glass. Mercury and glass. Okay, I'm taking the same diagram here. Let's say this is the mercury. Mercury is not of blue color, but still let's understand it. And this is the capillary, let's say. Okay, and you know that if the mercury is poured in it, or there is some contact, the mercury is like this, isn't it? The convex kind of thing. And if I take 2 points here, this is point B, this is point A, this is point D, some more points I am taking here, and this is point C. If you see here, this is like this. This point B is here, point A is here, and you should know the pressure at concave side must be greater than pressure at convex side. So now what happens? This PB is greater than PA, and we know that this PA is equal to PD, and it is almost equal to PC also. So what we know, that PB is greater than PC. Means though they are at horizontal level, equal levels, the PB is greater than PC. So now what will happen? The mercury will come out of this tube to balance this pressure, because we know that according to hydrostatics, the pressure at same level must be equal. So PC and PB, they must be equal, so that the mercury, it will what it will do, it will come out of this capillary, and after some time what will happen? This is the capillary, this is the mercury, and this is the surrounding mercury level. And now this is point B and this is point C. Now they are not at equal levels, because there is difference between them two, no? Okay, but here the point A will be here and they will be equal now. Okay, so this is all about fall of mercury inside a capillary, and this is about rise of water inside a inside a capillary. Just try to understand these concepts. Now the second concept, now we have understood why the water level or mercury level rise or fall respectively. Now we will derive an expression for the rise or fall. Okay, so for both the rise or fall, for both of them the expression is same. So we are not going to look at different cases, we are going to derive it using rise. Okay, going to derive it using rise means simply you are using water and glass. Okay, so we have seen that to balance the pressures or to make the pressures equal, the water or the mercury rush through the capillary and the level it either rises or falls. Okay, so I'm drawing the final picture. Let's say this is the mercury, this is the capillary, and this is the water, and this is the rise. So let's say this rise is equal to H. Okay, whatever the rise in the level, let's call this as H. Okay, and let's say this is point A, this is point B. Okay, so we know that to compensate the pressure, to compensate, say, the pressure difference, the rise or fall happens, isn't it? Whatever to compensate, or you can say to make it or nullify the pressure difference, you can say that, you can, to balance or to simply whatever you word you want you can use here, to balance the pressures, the rise or fall happens. So whatever the rise that is happened, okay, if you see here, that will be equal to the pressure difference, excess pressure difference. So if you take pressure at this point, see, it is very important now here. If you, let's say this is point, 1 minute, it will be little confusing for you if I write the same points here, A, B. So I am writing few new points here. Let's say at this point is called as P, let's say, and at the same horizontal level I am putting a point that is Q, and we know according to hydrostatic law, we know that pressure at P point should be equal to pressure at Q point, isn't it? Pressure at P point is equal to pressure at Q point. If you see pressure at Q point, it is equal to atmospheric pressure. So P naught is nothing but what? Atmospheric pressure. Okay, so we know this. Let's call this as point 1. So pressure at point P can be written as rho gh, okay, due to this, plus this atmospheric pressure. Okay, let's call this as equation number 1. At this point P, this P naught will be there and this rho gh will be there. So the combining pressure will be what? Rho gh plus P naught. Okay, if you take this point somewhere, let's call this as point R, and let's call this point as T. So the excess pressure difference between R and T is, we know that what is the difference. If you see here, it is only one surface here, and we have found it as 2T by R. Okay, this is the radius of this meniscus. Okay, it is like a drop or air bubble you can take. Okay, it is like an air bubble. Okay, so excess pressure is this, and if you say this rho gh is due to this excess pressure. Okay, so you can say that 2T by R is equal to this rho gh. Whatever the rise that is happening, it is due to this excess pressure, not due to this surface tension. So finally you can write this equation. Okay, every time you need not write these 2 points, you can directly write down the whatever the rise or fall that is happening, it is due to the pressure difference, or that is excess pressure. And for this meniscus, the excess pressure is given as 2T by R, where R is the radius of the meniscus. Meniscus means what? The water level, that is concave, convex, whatever it be. It is the meniscus. It is called as meniscus. So if you see, if you take this capillary here like this, and if you take this meniscus like this, the center of this meniscus may be somewhere like this. So this will be the radius r. Okay, and we know that this is angle of contact theta, isn't it? This theta is what? Angle of contact. Now you should remember it, this theta. Okay, and this r is always perpendicular to the tangent. So this theta means this will be 90 minus theta and this will be theta, because this is 90 degree. And this r is what? Radius of the capillary. So this small r is different and this big R is different. Just try to remember. So using this relation here, what I can write? Here I can write this r cos theta is equal to r. And simply this r is equal to r divided by cos theta. Okay. So I have this equation now, equation number 2, and this is equation number 3. What I will do, I will just put this value of capital R into this, and this will become from 2 and 3. What I can write? 2t divided by r divided by cos theta is equal to rho gh. And from this, if you want to find out this h, it will become 2t cos theta divided by rho g r is equal to h. And this is the expression for rise or fall, for both rise or fall. Okay, if they have given you the diameter, you will put d here, and for that here it will become 4. Okay, just try to understand. Okay, I think this expression is clear to you. You just remember here, the whatever excess pressure is here, due to that, see, this excess pressure is due to the surface tension, and due to surface tension the excess pressure, and that's why the rise or fall will happen. And whatever the rise or fall is there, that pressure difference, that is rho gh, will be equal to 2t by r. That will be the excess pressure. Okay, and so equating them and putting r is equal to r by cos theta, we will write this expression. That's all. Okay, this is called as expression of rise or fall using pressure method. This is what? Pressure method. Okay, and yeah, of course it is little confusing method, but if you get it, it is very simple method. Okay, to write. There are no much expressions, nothing. Okay, there is another method also, that is called as force method. That is called as force method. So this force method is also simple, but it involves a lot of not that much, but it involves little calculations and all. So we can use that also. So this capillary, generally these are not this much of diameter, they are really small, but for the understanding purpose we are writing here like this. Okay, drawing here. So this is the water. Now you must know, the whatever height here, okay, this much extra uplifted water, okay, lifted, no, it is lifted against the gravity. So why it is lifted? Due to the surface tension. So if you take a close look at this capillary, you will understand the surface tension. It is the force due to surface tension is always tangential. We know it, isn't it? The force due to the surface tension is always tangential. Okay, fine. So this is the force due to surface tension. Let's call this as Ft. And we know that this is angle theta, that is angle of contact. I am talking about water. If you take for mercury, it will be like this. You take any expression if you want, okay, like this, and 1 minute, and the surface tension force will be here, okay, and this will be the angle of contact, this complete, wait a minute, this will be angle of contact. So here it is little difficult to imagine and write the components of this, so better you go for water surface, okay, you go for this water surface. So, and this complete uplifted water, okay, this weight of uplifted water is balanced by the surface tension. See, whatever the weight is, whatever the amount of mass or amount of water that is uplifted, it is lifted against the gravity, otherwise it will come to the normal point, and it is lifted by this what? Surface tension. And if you take the components, this will also be theta, this will also be theta. If you see here, these will be two components like this. So this will be Ft sin theta, and this will be Ft cos theta. Here also it will be Ft cos theta, and this will be Ft sin theta. Okay. So here whatever the mg weight is there, whatever the mg weight of this it is there, it is balanced by Ft cos theta. Okay. So now here one misconception is there. So many students will think that, sir, why only Ft cos theta? It is Ft cos theta plus Ft cos theta, it should be 2T cos theta, 2Ft cos theta, na? See, if you see in 3D shape, okay, this shape is like this, and from every direction is pulling, the Ft is pulling, okay, it is not from only two directions, from every direction the surface tension pulls. So combining force I have written it, this is what, this is 3D force. From every direction, this Ft, this is Ft, this is Ft, this is Ft, and all this force combiningly I have written it as Ft. It is not that it is acting only at these 2 points. See, there is complete circle here, and at every point this Ft is acting. Are you getting it? And so the summation of these all Ft cos theta, I have written this as Ft cos theta, all the summation. Okay, just try to understand this. Okay, so we have this expression called mg is equal to Ft cos theta. This is equation number 1. Now what is this mg? Okay, let's talk about this mg. This can be written as rho g or v rho g. This m can be written as volume into density into g. So we know the density of water, we know the acceleration due to gravity. What we don't know is the volume. Now volume can be written as area of cross section into height h. So here area of cross section for this uplifted water is pi r square, isn't it? So here it is pi r square into h. So finally what we can write, this mg or the weight of this water which is being uplifted here, it will be equal to pi r square h rho g. Let's call this as equation number 2. Okay, this is very simple. Whatever I have done this in second step, you just try to understand what I have done. Now third, this Ft cos theta. What should we do with this Ft cos theta? This is also important. Okay. So you must understand this Ft is what? This is T into L. Okay, and this cos theta multiplied here. Isn't it? We have seen it. And this Ft is acting for this complete circumference, that is 2 pi r. So this Ft cos theta, it will become T into 2 pi r into cos theta. Let's call this as equation number 3. Okay. If you equate or from 1, 2, 3. If you check it out, what will happen? This T into 2 pi r into cos theta will be equal to this mg. That is what? Pi r square h rho g. Okay. So if you, this pi gets cancelled out, this r gets cancelled out, this power. Okay. So if you see, if you want to find out this h here, this h will become 2t cos theta divided by r rho g. We are getting the same expression for either fall or rise. Okay, just try to remember, try to understand this. Okay, see this complete surface tension force is acting like this. That's why we have taken this effective length. I have taught you once. Okay, you should not forget this, and this will become 2 pi r. Okay, this L means effective length. Here on this complete circumference the force is acting. Okay, here like this. Let's move to the next question, that is critical velocity and Reynolds number. These are interconnected concepts, Reynolds number and critical velocity. You will learn more about these concepts in your engineering if you are opting for it. Otherwise, let's have a brief look at these both concepts. First, you should know, let's take a revision if you have studied it. Okay, first you should know there are many kinds of flows like streamline flow, laminar flow, turbulent flow. You should read them first, then you come to this video. Okay, because I am not taking those concepts here because those are self-explanatory. So if you look at this concept, that is streamline flow. So this is one kind of flow in which, see, fluid is what? Fluid is actually in the fluid particles, the particles move in layers. Okay, so let's say there are few layers like this. Okay, this is layer 1, 2, 3 and this 4. So streamline flow means what? This layer will not mix together. Okay, the fluid will continue to move in layers simply. This is also called as laminar flow. Means it is very smooth flow. This is also called as sometimes smooth flow. Contrast to this, if you take one more flow, that is called as turbulent flow. Okay, so in this what happens? These layers get mixed. Okay, and there will be turbulence, complete turbulence like this. Okay, the layers mixing will be there. And this streamline flow, if you start the pipe, the flow in the pipe, let's say this is a pipe, this is a boundary of this pipe we are talking about. If you start the flow of water, and if the speed or flow speed or flow velocity, if the flow velocity is less, you may get this streamline force, or this flow velocity is if high, there will be mixing of these layers and you will get this turbulent flow. So these types of flow, whether it is streamline flow or turbulent flow, they are majorly depend on this velocity. Which velocity? Flow velocity. Okay, so if you see, there should be a velocity or there should be a boundary. Okay, like this, and you should specify a velocity like 100 meters per second. For example, I am talking before 100 meters per second, if the velocity is there, okay, if the flow velocity is below 100%, the flow will be streamline, means it will go in these streams. These layers are also called as streams. And if it is higher than this, it will get converted into turbulent flow. or it will no longer remain the streamline flow. And this boundary or this velocity is called as critical velocity. It is called as the critical velocity. So what is this critical velocity? It is simply written as Vc. It is the velocity beyond which streamline flow, SLF, I am simply writing as streamline flow, gets converted into turbulent flow. Okay. So every time you cannot measure or the flow velocity, or you can measure it, but sometimes the diameter of the pipe is also playing some crucial role. Sometimes the liquid you are using, whether it is water or oil or honey, its density, that is also matter. Its viscosity also matters. So for that, this flow only does not depend on this critical velocity, but it also depends on these factors, like let's say d is the diameter of this pipe, dia of the pipe. Okay, we know that Vc is the critical velocity. Okay, now critical velocity, that concept is over. It is the velocity beyond which streamline flow gets converted into turbulent flow. Now we are looking at Reynolds number. What is the Reynolds number? So this conversion, it is majorly depend on this critical velocity, but it also depends on the diameter of the pipe, whether it is large. If the pipe is very much large, the turbulence is bound to occur. It will occur. If the pipe is like capillary, the flow will be streamlined for any velocity. Okay. If you take the density, it will also depend on the density, whether you are looking at the clean water or honey or oil. Okay, for clean water the turbulence will happen easily. For oil the turbulence is not that much easily happening. Okay, so these are some points, or you can call the viscosity also plays important role. So using all these parameters, these are all parameters that decide nature of flow. Okay, these are all the parameters which will decide the nature of flow. So every time you cannot find out what is the density, what is the, or so if you combine all them, you will form a number, you will form a dimensionless number, and that is called as Reynolds number, simply written as R. Okay, so Reynolds number is the number that will simply decide, okay, that will give you an idea about the nature of the flow. Okay, if it is lesser than 1000, the Reynolds number is less than 1000, you can say that the flow is streamline. If it is greater than 2000, you can simply say the flow is turbulent. Okay, so this is what, 1 minute, whatever given in the book I'm telling you accordingly. Okay, because in mechanical engineering, if you take it, the values are slightly different, 2300 like that. So here, as per the book, the Reynolds number is, if it is less than 1000, the flow will be streamlined. If it is greater than 1000 or 2000, flow will be turbulent. If it is in between somewhere, it is making a transition from streamlined to turbulent. Okay, so there are three types of flows. First one is streamline, second one is transition flow, means here you cannot decide the flow is streamline or turbulent, and third one is what, turbulent. So for this streamline, the Reynolds number is less than 1000. For this transition, the Reynolds number is less than 2000 but greater than 1000, and for this turbulent, the Reynolds number is greater than 2000. Okay, so how this Reynolds number is given? Okay, how this, the formula for Reynolds number The formula for this Reynolds number is given as Vc, that is critical velocity, into rho, that is density, into d, that is diameter, or simply you can write capital D if you want, divided by mu. Okay, so see, if the diameter is higher, the Reynolds number will be higher, and it is more susceptible to occur what? Turbulent flow. Okay, you can also say that now density and viscosity, you might get confused here, but let's not talk about the density. If the viscosity is higher, like for honey if you say, and viscosity is lower comparatively for water, if you give same flow velocity for both of them, water will be turbulent but honey will not, because of its viscosity. Okay, just try to remember this. The Reynolds number simply is the pure number. It has no unit, nothing. It will simply decide the nature of flow. It is made for deciding this nature of flow. Here the nature of flow depends on this Vc, d, rho, mu, but every time you cannot calculate them, every time you cannot calculate the flow velocity and all. For that, simply one chart is made. On that the formula like this is given, Vc rho d divided by mu, and this complete term becomes dimensionless, and it gives us simply a number, like whether it is 1500, 2000, whatever, and based on that you will decide what is the nature of this flow. Okay, if you put these values, and if it is coming like 300 or 400, you can simply decide it is a streamline flow. Okay, if it is coming up to be 1200, you can simply tell them that it is neither streamline nor turbulent, it is in transition period right now. If you increase the velocity, the Reynolds number will increase. If it is more than 2000, it will be turbulent flow. This is simply the concept of critical velocity and Reynolds number. Try to understand this. Now we will talk about the important concept, that is Newton's law of viscosity. It is a very simple concept, but there are some assumptions you should keep in mind for this. So before that, we should look at what is the viscosity. So for your understanding only, I am telling you. So let's say this is a solid surface, okay, on which this is the liquid that is flowing. This is a liquid that is flowing. So this viscosity law, it majorly holds true for laminar flow. It holds true for laminar flow only actually. So these are the layers, let's say, because we know that laminar flow means these are streamlines, or these are layers in which the fluid is flowing. So what happens here, when the liquid and solid surface gets in contact, there will be some adhesion here. There will be some adhesion, and due to this, if the top surface is moving with 2 meters per second, let's say, and the bottom surface, due to adhesion, it is at rest, let's say, there will be friction acting at these interfaces. Are you getting it? Means this is moving and this is at rest. This is what 0 meters per second. Practically I am saying, ideally I am saying it is at 0 meters per second. And in between, the layers are moving, like this might be moving with 1.5, this might be 1.0, this will be 0.5. So you are moving from, as you go away from the surface, as the distance is increased from the surface, the velocity is changing. Okay, and this is called as velocity gradient. Velocity gradient. Let's say this is distance x and this is the velocity. For every small change in distance x, there will be small change in distance velocity dv, and we put a mod here. This is what mod, to show its magnitude only. We are not interested in whether it is increasing or decreasing. Simply we are writing dv by dx, and this is called as velocity gradient. Why it is happening? Due to, first, this is due to adhesive forces, and if you take any two layers, this is layer 1 and this is layer 2, let's say, there will be a relative motion. See, this is moving fast, this is moving slow. Means there is a relative motion between these two layers, and the bottom layer will drag it backwards, and that dragging force or the dragging property is called as viscosity. So simply you can say viscosity is a property of fluid by virtue of which the relative motion between two different layers, okay, or the relative motion between two layers is minimized or it is opposed, and due to the dragging force, and that dragging force is simply called as viscous force or viscosity. Okay, this is all about viscosity. And due to this viscosity there will be a velocity gradient inside the fluid. Okay, and the Newton's law of viscosity, the statement goes like this: for streamline flow, it holds true for streamline flow only. For streamline flow, the viscous force acting on any layer, the viscous force acting on any layer, you take any layer in this, the viscous force, it is directly proportional to first velocity gradient. Actually, due to that velocity gradient, due to that force only the velocity gradient is there, but we are simply establishing one proportionality here, that whatever the force is acting here, that simply shows the velocity gradient. It is directly proportional to the velocity gradient, and also it depends on the weighted area. Weighted area means the contact area. Let's say call it as A. So this viscous force Fv is dependent on this velocity gradient that is given as dv by dx, and it is also dependent on this weighted area that is A, okay, or area of the layer you can say. And for that we can write this, it is simply equal to A in bracket dv by dx. Okay, simply this is magnitude of the viscous force. If you take it negative, it shows that it is dragging behind or it is pulling it behind. I am simply using modulus here, and this viscous force simply is equal to Na dv by dx. Sorry, not Na, what I am doing, this is eta, this is called as eta, and this is to show the coefficient of viscosity. And this eta shows how much the friction will be there. Okay, if you take for water and if you take for honey, eta for honey will be higher than that of the water. Just try to remember, and this is the mathematical expression for Newton's law of viscosity. Okay, now we will study about the Stokes law and terminal velocity. For JEE mains and NEET also, this is very important because there are many questions here, but for the boards we are interested in the derivation of this law. This is very simple actually. We'll go by the textbook derivation. So actually there are many scientists who contributed in fluid mechanics. So there were two scientists called Navier and Stokes. Among them one Stokes law is here, and it is very simple. See, if we what we will do, we'll take one liquid here, okay, and this Stokes law, it is used to determine many things like viscosity of a liquid, like that. Okay, let's say there is a small sphere. This is what, a small sphere, and it is falling through this liquid. Okay, it is coming down inside this liquid, and when it is coming down, what will happen, this liquid will apply some dragging force on it, or it will apply some viscous force on it. isn't it? It will oppose the sphere. And the Stokes law states that the viscous force acting on a small sphere falling through this liquid is directly proportional. First, it is directly proportional to the radius of the sphere. Next, it is directly proportional also to the velocity. Let's call this is velocity through which it is falling, velocity. And it also depends on the coefficient of viscosity, or simply viscosity. Okay, coefficient of viscosity. And this is the statement of Stokes law. He says that this Fv is proportional to eta Rv. And if you write down the mathematical expression for this, if you remove this proportionality constant, the final answer comes out to be like this: 6 pi eta Rv. So here this 6 pi is the proportionality constant. This is using the experiments. They have written this constant that is equal to 6 pi. So finally, if you take this review, this viscous force depends on the viscosity, the radius of the sphere, and the velocity of the sphere. Okay, this is the Stokes law. I'm not writing the statement here, but this is the proportionality, this 3 proportionality, this complete is the statement of his law. Okay, now we'll talk about the terminal velocity. Is a very simple concept actually. It needs your imagination here. Now we have seen the Stokes law, that the viscous force depends on the velocity. It depends on the velocity, radius, eta. Those all things are fixed. But here, if I am taking the same liquid, the eta will be constant. Okay, if I am taking the same sphere, the r will be constant. What is changing throughout the motion? That is velocity. So that's why I am written here that viscous force is directly proportional to this velocity. It also depends on these things, but we have made them fixed. Okay, so initially, let's say the velocity here, the velocity was vi. Okay, or yeah, it was vi. And the velocity vi was very less, let's say, or 1 minute, we'll call this as okay, whatever, the velocity I was there, and the viscous force initially it was 6 pi eta Rvi. Okay, now when it comes in the liquid or in this medium, there are few forces acting on it. There will be a buoyant force, or buoyancy or upthrust force, which is equal to V rho g, if you remember it, where V is the volume of the sphere, rho is the density of this liquid, and g is the acceleration due to gravity. Next, gravity force will act. It is equal to mg, or it is equal to rho vg, where rho is the density of that object. See, this is the density of liquid, this is density of the object. Your volume will be the same, but here you must remember the density of the liquid and density of the object. Or simply what I will do, I will take this density of object as rho, and density of liquid as sigma. Okay, density of liquid as sigma. This is density sigma and this is density rho. Okay, volume is same. Volume for both of them is, for both the calculations, the volume is same, but the densities are different. And the third force we are talking here about, this, that is viscous force. This will be 6 pi eta Rv. Okay, so what will happen when it comes downward? Okay, it is coming in. What will happen? This viscous force will gradually reduce its speed. This buoyant force also and this viscous force, they are acting against this gravity force. If you take the FBD, free body diagram of this sphere, the gravity force Fg will be downward, the upthrust Fu, and this viscous force they will be upward. So means there is this balance. Okay, not balance actually, because it is moving. So initially this viscous force, maybe it is not that much high. Okay, so it will gradually what it will it will try to reduce the speed. Okay, and there will be a time that this sphere V, it will have a maximum speed. Okay, means what? Sorry, there will be a time, I'm sorry, I'm just taking these steps here, that's why, because if I'm teaching in my own style, it will not take this much time. I'm teaching as per the guide now, so that's why it is little hectic for me, but still, see, this is the velocity V. Okay, so when it comes, okay, downwards, up to this point the velocity changing, and now what will happen, the velocity will be constant when it is falling through the, because there is a maximum force, or there will be a time when these all forces are balanced, like we have seen in the current electricity drift speed, when all opposition and the accelerating forces are balanced, there comes a time in the terminal, that is terminal velocity. Okay, so if you take this graph for this, you will better understand using a graph here. Initially the speed was Vi, and it is reduced substantially, and finally it is like almost constant. All the forces are balancing each other, and this is called as terminal speed. Okay, due to all opposition and all is done here, and now here if you see, all forces are balanced. Okay, and when it is balanced, the viscous force acting on it will be equal to 6 pi eta r vt. This is terminal velocity. The upthrust, it will be equal to buoyancy is what, sigma vg, and the fg will be equal to rho vg, and these all forces are now balanced at the terminal. Initially they were not balanced, so that the viscous force was there acting on it, it was continuously reducing it, retarding it. Finally time comes when the velocity is reduced in such a way that all the forces are balanced, and the velocity and the sphere is moving with a constant speed, constant velocity, and that constant velocity is called as terminal velocity. So you can write down the definition of this terminal velocity. This terminal velocity is the constant maximum velocity acquired by the body falling through a viscous liquid. So initially you have thrown the body inside the liquid with 100 meters per second, let's say. Finally all forces are balanced, and at that time maybe it is moving with a constant speed of 2 meters per second, because up to this point the viscous forces, the buoyancy forces, all have reduced this velocity to a constant velocity, and at this point the net force acting on this body should be equal to 0, means all the forces must be balanced, and that constant speed is called as terminal velocity. And at this point you can also define it as the net force on the body will be equal to 0, so that it is moving with constant velocity. So if the forces are balanced, what you can write, that viscous force plus this upthrust or buoyant force is equal to gravity force, isn't it? Gravity is pulling inside, and those are opposing it. So this viscous force is what, 6 pi eta rv, but here we are talking about the terminal condition, so I have written is Vt. If you take this buoyancy force, it is equal to sigma Vg, and if you take this gravity force, it is equal to rho Vg. Now rho is for density of object and sigma is for density of liquid. Okay, this much expression is remaining right now. So we know that the volume of the body is equal to 4 by 3 pi r cube, isn't it? So write it down, 6 pi eta r Vt plus sigma into 4 by 3 pi r cube into G is equal to rho into 4 by 3 pi r cube into G. So if you take this term here across the boundary, it will become 6 pi eta r Vt is equal to, here this 4 by 3 pi r cube G rho minus sigma is there, isn't it? So this much expression will be remaining here. Okay, 1 minute. Yeah, correct. So this pi gets cancelled out, this r here it will become square. Okay, and if you divide it, it will become 2 3s are 6, 2 2s are 4, and finally this will become 3 eta Vt is equal to 2 by 3 pi r square G rho minus sigma. And this 3 eta, if you take here, it will become Vt is equal to 2 by this 3 into this 3, that is 9. Okay, I will write it using the same, no, this pi will not be here, no? Yeah. 2 by 9, and here I am going to write it as per the book. It will become r square G rho minus sigma divided by eta, and this is the formula for terminal velocity. Okay, you should remember this formula for board examinations, and if you don't remember this formula for JEE, it doesn't matter, because if you are clear with this logic, if you are clear with this balancing of these forces, you can solve it from here also, putting the respective values. No need to mug up this big formula for JEE or NEET. You can for boards you need to derive it, isn't it? Or you must know this formula. Okay, because sometimes direct question may ask. Okay, so this is all about mechanical properties of fluids. Okay, there are 2 videos. If you haven't checked the last video, check it out. Okay, and before watching these kind of videos, you first should read the chapter on your own, whatever it be. Basic concept should be clear, then you can go for these higher derivations and all. Okay, so have a good day. Bye bye, take care.